This is a microchip, and when you zoom in, what you find isn't a flat slab of silicon. You find a city, a nanoscopic metropolis with skyscrapers hundreds of layers tall, roadways made of copper thinner than bacteria, hundreds of kilometers of wiring packed into something smaller than your fingernail. And at the very bottom of this city are billions of tiny switches, transistors, on, off, 1, 0. Every photo you've ever taken, every message you've ever sent, every AI model you've ever used, all of it comes from these switches flipping billions of times per second. And here's the secret. The smaller we make those switches, the faster computers become. Signals travel shorter distances. More transistors fit into the same space. Power explodes. For over 50 years, this shrinking followed a simple rule. Every 2 years, the number of transistors on a chip doubled. It became known as Moore's Law, and it built the modern world, until it almost died. Moore's Law hits a wall. Around 2015, something terrifying happened. The industry slowed, then stalled. Transistors stopped shrinking at the same pace. Physics pushed back. Heat, quantum effects, light itself became the enemy. For the first time in half a century, the engine of progress began to fail. And without a breakthrough, computers would stop getting faster. Phones would plateau. AI would stall. The digital future would freeze. But Moore's Law didn't die, because one machine, built by one company, did something almost nobody believed was possible. This is the story of the most complicated commercial machine humanity has ever built. The impossible machine. Let's try a thought experiment. Imagine you're shrunk down to the size of an ant. You're floating inside a vacuum chamber. In front of you, a droplet of molten tin, smaller than a human cell, is fired past your head at 250 kilometers per hour. Your task? Hit that droplet with a laser. Not once, not twice, but 3 times, within 20 microseconds. And when you hit it, you must heat it to 220,000 Kelvin. That's 40 times hotter than the surface of the sun. Now repeat that 50,000 times every second. And never miss. That's not science fiction. That's reality. That's happening right now. Why this machine exists? This machine exists for one reason: to shine light onto silicon, with precision down to 5 atoms. To do that, it uses a type of light so extreme that air absorbs it, lenses absorb it, glass absorbs it. Only perfect mirrors can reflect it. And those mirrors, if scaled to the size of the Earth, the largest bump would be thinner than a playing card. That's how smooth they are. And while all of this happens, parts of the machine accelerate faster than a Formula One car. For 30 years, engineers said this machine was impossible. They were wrong. How chips are made. To understand why this matters, we need to understand how microchips are made. It starts with sand. Silicon dioxide is purified until it's nearly perfect, then melted. A single seed crystal is dipped in and slowly pulled upward. Atoms lock into place. A flawless cylinder of crystal silicon grows, called an ingot. That ingot is sliced into thousands of wafers, each wafer polished until it's nearly atomically flat. Then the real magic begins. Coat, expose, deposit, again, and again, and again, layer after layer after layer. Some chips have over 100 layers. And the hardest step? Shining light through a pattern onto the wafer. This is photolithography, and it's where everything breaks. Light becomes the enemy. At first, lithography seems simple. Light goes through gaps, blocked where you don't want it. But when those gaps become as small as the wavelength of light, physics rebels. Light bends, waves interfere, patterns blur. This is diffraction. And diffraction sets a hard limit on how small you can print. For decades, engineers fought this by using shorter wavelengths. Eventually, the industry settled on 193 nanometer deep ultraviolet light, and that carried us until around 2015. Then we hit the wall. To go further, we needed light 10 times shorter. Light so extreme, It doesn't exist naturally on Earth. Extreme ultraviolet. The crazy idea. In the 1980s, a Japanese scientist named Hiro Kinoshita had a wild idea. What if we used X-ray-like light? Wavelengths around 13.5 nanometers. In theory, it would allow features unimaginably small. In reality, everything absorbed it. Air absorbed it. Glass absorbed it. Lenses absorbed it. Even mirrors absorbed it. So the world laughed. But Kinoshita didn't stop. Because someone else had discovered something extraordinary. The smoothest objects ever made. Physicists figured out how to reflect X-ray light. Not with normal mirrors, but with multi-layer mirrors. Dozens of alternating atomic layers. Each layer only a few atoms thick. Together, they reflected light that should never be reflected. It barely worked. Only a few % of light survived. But it proved something crucial. EUV lithography was possible. Still, no one believed it could scale. America's nuclear labs enter the story. Across the Pacific, inside U.S. nuclear weapons labs, scientists studied fusion reactions. Fusion releases massive amounts of X-ray energy. And suddenly, those impossible mirrors had a purpose. Engineers tried to turn nuclear physics into chip making. They failed. They were laughed off stages. Funding was cut. Entire teams quit. By the mid-1990s, EUV looked dead. Until the semiconductor industry panicked. The industry makes a desperate bet. Intel, AMD, Motorola. They knew 193 nanometers lithography would fail. So they did something unprecedented. They pooled hundreds of millions of dollars to keep EUV alive. And by 2000, the prototype existed. It worked. Barely. 10 wafers per hour. Commercial fabs needed 100 plus. Most companies walked away. Only one stayed. SML, the company that refused to quit. SML, a small Dutch company born from Philips. No glamour, no hype, just engineers. They partnered with Zeiss for optics and bet everything on EUV. They needed a light source, and that's where things got insane. Building an artificial sun. To generate EUV light, you must create plasma hotter than the sun. SML tried gas. Failed. Then they tried tin. Molten tin droplets. Fired at high speed. Hit with lasers. Exploded into plasma. It worked, but it destroyed mirrors. Coated them in debris. Killed productivity. The mirrors had to last a year. 1 nanometer of tin would ruin them. So ASML invented something unbelievable. They filled the chamber with hydrogen. The hydrogen cooled the debris, carried it away, even cleaned the mirrors while running. But that hydrogen exploded. 50,000 microsupernovas per second. Engineers had to model shockwaves like astrophysicists. This wasn't chip making anymore. This was cosmic engineering. The breakthrough that saved everything. Then came the breakthrough. Instead of hitting the tin droplet once, hit it twice. First pulse, flatten it into a pancake. Second pulse, vaporize it completely. More light, less debris, higher efficiency. UV crossed 100 watts, then 200 watts, then finally, commercial viability. The most important machine on Earth. By 2016, orders flooded in. Every advanced chip now depends on this machine. Costs over $350 million. Ships in 250 containers. Flown on 7 Boeing 747s. Inside it, mirrors aligned to picoradians. Layers aligned within 1 nanometer. 5 atoms. That's the margin of error. Every smartphone chip you use passed through one of these machines. Why this matters? This machine didn't just save Moore's Law. It saved AI progress, smartphones, data centers, modern computing itself. Took 30 years, thousands of failures, billions of dollars, and a refusal to accept impossible. Because progress doesn't come from reasonable people. Comes from unreasonable ones. If everyone had been reasonable, none of this would exist. No smartphones, no modern medicine, no AI. The world would be smaller, slower, and far more boring. So maybe the lesson is this: be unreasonable, at least when it matters, because sometimes the future depends on it.